Good morning. Thank you for coming. I'm Andrew Noble. It's me. And that's Raf. I'm doing the first half. He's doing the second half. So, all right, the title of the talk is Memoryless Sequences for Differentiable Losses. I'm going to skip the outline and go right to background and motivation. I think that'll be clearer. So, the question we were interested in is the following. Imagine that I'm giving we're in an individual sequence setting. So I'm given a sequence Y, whose elements Y1, Y2, and so on are vectors, but for simplicity, you can think of RD as just being R. And we were interested in the following questions. Now, these questions are not new by any means, and we're not claiming that we've answered the questions, but it was just about asking them. So the first question is, when and in what sense can an individual sequence be called random? Obviously, there's a huge literature on this, and this is not the focus of the talk, but our interest was in looking at the second question and seeing what it has to do with the first. So the second question was this: when and in what sense can I call this fixed sequence unpredictable with respect to some loss that may be of interest to me? So we know that if a sequence is random, if I really have an ID sequence of coin flips, then of course I expect that I can't predict it. Except perhaps in some sense if I know the probability that the coin is going to show up heads, then under the squared loss that would be my prediction. But beyond that, there's really no point in looking at the past sequence of flips to predict what's going to happen next. So the idea here is, if we have a sequence which is unpredictable, if we turn the question around, in what sense should it look random? Okay, so that was kind of the motivating question, was to look first at unpredictability and then see what follows in regards to something we could call random behavior. So, overview here. We're interested in investigating asymptotic connections between unpredictability and randomness. So we have a definition of unpredictability. That's memorylessness. It's asymptotic, and the conclusions we can draw from that in regards to random behavior are also asymptotic. So I realize a lot of the talks here have had finite sample results. We won't have those. We're going to have lim-imps, lim-sups, or just limits. All right. So in particular, the work on this, I had written a paper on this 11 years ago, which has been cited twice. All right, so not incredibly popular, but I did that for the squared loss, and I realized when I met Raf some time ago that he was the right guy to ask about what could be done for more general losses. So and stuff changes. So when you move from the square loss to, say, Bregman divergences or more general differentiable losses, the story changes in ways that we think are interesting. And in particular, and why we're in the session, there are connections with elicitation, which Raf will discuss a bit later. So here's the setup and assumptions for the entire talk. Our prediction space X, the space in which we're making our predictions, is just an open and convex subset of RD. The outcome space Y, in which the sequence takes its values, okay, that's going to be compact, so closed and bounded. And we're going to assume that our loss is continuous. We have a loss from X cross Y to R. In general, it need not be non-negative, but you can assume it is. And the loss has two critical properties that we use numerous times. The first is that if I fix the second coordinate Y, the loss is convex in the first coordinate. And the second assumption is that if I look at the derivative of the loss with respect to the first coordinate, it's continuous and it exists. Okay, so when you see gradient L of X, this is the gradient with respect to the first coordinate. Okay? All right. So with that, I can now define this notion of unpredictability, which we call memorylessness. One preliminary definition. So to define this notion, we're going to look first at a family of possible prediction rules that are very simple. So let's CK be the family of bounded continuous functions from YK. So that would be, imagine K observations, K elements of my sequence, that map into X, which is my prediction space. Okay? So this corresponds, if I'm trying to make a prediction, I'm looking along my sequence, I'm trying to predict what's going to happen at time t. I look at the k previous values, I apply this bounded continuous function, and I let that be my prediction of the next value. C0 is just going to be the family of constant functions. And so the definition we have of being unpredictable is this. It's pretty simple. So it says that there's some constant c in X. X is my prediction space. This represents, at time n, the average loss of the predictor who ignores the sequence and just says every time C, right? right? Don't bother me. Or it just says C. It puts C on its office door and it goes home, right? So it's on vacation, right? This represents somebody who's chosen a window K and is using a bounded continuous function of the K previous values to try to predict what's going to happen next. Okay, this is their average loss. So what this says is essentially just go home, right? There's really no point in trying to be more clever than the constant predictor. So it says that if I look at the difference of those average losses and I take a lim-inf, that lim-inf is greater than or equal to 0, which essentially means that this guy is doing no better than this guy. Is everyone okay with that? So again, I'm quantifying over every K, that's every block length, every continuous function. All right, so again, we can regard these functions G as being continuous kth order Markov predictors. Okay, Markov in the sense that I'm just using the K previous values of the sequence to predict the next value. The continuity here, it works out well. We'll see, we're going to talk about weak limits. So if you remember your probability class, you talk about weak convergence, you have bounded continuous functions. So there's a nice match there. But also continuity prevents pathologies. If my y's take values in a real valued space or something that's infinite, and in particular if I have a function that's just measurable or whatever and not continuous, then it can predict well even though it's not really predicting well. So the continuity here gets rid of pathologies. All right, so another way of saying this is the sequence is memoryless if no finite order predictor can outperform the optimal 0th order predictor, which just says C. Okay. So two probability things which we're going to need for our results. The first is the notion of weak convergence. Again, I presume you've all seen this at some point, but here's the definition. So I have a sequence of measures on Ym. That's just the the m-fold Cartesian product of y with itself. That sequence converges weakly to a probability measure nu if the integral of every bounded continuous function under nu n converges to the integral under nu. Okay? So in the vectorial case, I have a convergent sequence of vectors. In the real value case, it's a convergent sequence of numbers. All right. And importantly, the limit nu, remember, the limit nu is the probability distribution on Yn. I can regard that as the distribution of a sequence of random vectors, y1 up to ym. And I will do so in the future. So if I speak about the weak limit of a sequence in script ym, I can regard that just as a sequence of random vectors. And that's going to be important in what follows. All right, so what are our nu n's going to look like? Here, the nu n's are just going to be the empirical measures of y. So just to be clear, if I fix m is like a window width. I look at y1 up to ym. That's a point in script ym. And then I look at y2 up to ym plus 1, y3 to ym plus 2. So I take this window and I just slide it along my sequence. And at every instant, I have a point in ym. And I can look at n shifts and assign each one of those shifts a measure 1 over n. That gives me an empirical measure on this family. Okay? And that empirical measure is just defined like this. For set A, I just count the number of shifts that fall in that set A. Is everyone okay with this? Again, this is and when people are looking at stochastic properties of individual sequences, this is pretty much what they're doing. So there's nothing particularly new here. Thank you. Okay. I will hurry because I don't want to eat into Raf's time. All right, so let me give you a brief overview of what the results say in the square case. So in the square case, we have the following. So it turns out if a sequence is memoryless under the squared loss, then every weak limit of its empirical measures is a martingale difference, or really a shifted martingale difference, where the shift is the constant C, right, that is the best predictor. So that's expressed here. And again, there may be many weak limits of those empirical measures, maybe uncountably infinitely many, but what this says is any one of those limits, and they can be different, has this property, right? It corresponds to a shifted martingale difference sequence. And so with that in hand, we can now extract some asymptotic stochastic properties of the sequence in this way. So for example, we get a law of large numbers, where not surprisingly, the average of the y's converges to C. And we get here something like a sliding block central limit theorem. What does this say, right? I look at a block of length m, I add up its values, I multiply by m to the minus 1/2. If m is big, and if I look at a lot of shifts, right, I look at the empirical measure of this family of numbers, right, its empirical measure is approximately normal. Okay, and then one can also say something about Azuma-Herfting. All right, so I don't go too over time. Let me just pass this on to Raf, and this is a little bit more about what he's going to talk about.
Thanks, Andrew. Right, so to connect with elicitation, let's first recall some of these definitions. So let script P be some convex set of probability distributions over our outcome set Y. We say that a property is just any function that assigns to each probability distribution some correct prediction or report for that distribution. And we'll say a loss function elicits a property if for every distribution in the set script P, when the outcome Y is drawn from P, the unique minimizer of the expected loss is gamma of P. It's the correct prediction. So for every distribution over the outcomes, the minimizer of the expected loss is just gamma of P. In that case, we say the loss elicits gamma. And as will be relevant, of course, the squared loss elicits the mean. So meaning that when Y is drawn from some distribution P, the unique minimizer of the expected square loss is just the mean under that distribution. Okay. Squared loss is a special case of the family of Bregman divergences where you take a convex function G, and here I've swapped the order of the arguments. So the Bregman divergence is just the difference between G evaluated at the outcome Y and the linear approximation of G from the point X evaluated at Y. And it's well known that basically a loss elicits the mean if and only if it takes this form up to some function of Y. So the full class of loss functions that elicit the mean are the Bregman divergences. And so when I first saw Andrew's paper from 11 years ago, I thought, well, maybe the elicitation is what's driving these results, that the fact that you get martingales and all of these stochastic properties is really because the loss function is eliciting the mean. And so that was the question, do these results, in particular the law of large numbers, this central limit theorem and all these things, do they hold for a broader class of loss functions, such as the Bregman divergences? And in fact, this is the case. So for any Bregman divergence, if you replace squared loss with a Bregman divergence, you get the same results. And interestingly, while our main theorem will require convexity, there's a trick in the case of Bregman divergences where if you move to the mixed divergence and then back, you can get this to hold even if the Bregman divergence is non-convex in X, which is usually the case. Okay, so the main result is a generalization of this for any loss function. So this is the result. So a sequence, an individual sequence, is L memoryless with respect to C if and only if this condition holds. So for every M, the M area weak limit of the empirical measures is stationary and bounded and satisfies this equation 1, which is just saying that the expected loss is minimized by this constant C, where the outcome is drawn as yk conditioned on y1 through yk minus 1. So just as a quick example, as you might hope, if you do indeed have random vectors that satisfy this equation, this relation for all k, so for each k conditioned on the previous y's, C is still the minimizer of the expected loss, then indeed with probability 1, the sample paths of this sequence will be L memoryless with respect to C. This statement looks a lot like the elicitation definition of L eliciting something, and so we get as a special case, if two losses elicit the same property, so that the minimizers of the expected loss are both described exactly by gamma, then they have the same memoryless sequences. So in a sense, this is saying that the one-shot properties of the loss are describing this sort of infinite notion of memoryless, that all you really need to understand the memoryless sequences are what the loss elicits. So the main tool that we use to prove this is this notion of orthogonality, which I'll briefly describe. So it says that if you have some bounded sequence and some family bold X of bounded sequences, then basically the memorylessness condition with respect to this family bold X, which says that you can't do better than just predicting C asymptotically, that statement is equivalent to this sort of orthogonality condition, which says that the gradients of the loss dotted with the difference between the X's and C, that goes to 0 asymptotically, that average. And you could think of this as sort of a first-order optimality condition for this objective. And I think, so I'll prove one direction, which is the easy direction, which I think illuminates this a little bit. So let's assume 2 and show 1. So just writing out one of these n terms, you have that because L is convex, the difference between L at xi and L at c for fixed yi is lower bounded by the subgradient. So this is just a subgradient inequality. So the derivative of L at c dotted with xi minus c. So this is just falling from convexity. But of course, if we sum over I and then divide by n and take the lim inf, on the left-hand side we get this left-hand side, and the right-hand side we get this expression, which if we assume 2 is 0. So if this condition holds for every x in our set bold X, then we immediately get our memorylessness. Okay, and for those of you who are familiar with prediction markets, I'll just very briefly give a quick application of this. So if you set this particular loss function where you have some securities phi I, some convex cost function ci, and x is the number of shares in the market, the gradient of c is the current market price. Long story short, if you take the orthogonality condition, this lemma, and you just plug in that loss function, you get this interesting statement that says, for such a prediction market, this expression, if you're familiar with prediction markets, is the cost to the trader of buying xi minus c shares. And this expression, well, this is the market price, which is set to the gradient of c at little c at each time. And basically this is saying that there's not much profit in the market if and only if the prices of the market are calibrated in some sense. So if you've seen prediction markets, we get an interesting application there. But let me wrap up. So we were looking at individual sequences and the connection between unpredictability and randomness. We were able to generalize previous work for the squared loss to general Bregman divergences and beyond, and acute application to prediction markets. Thanks.
All right, so we have time for questions. Yeah. So. Can you repeat the question?
So could we extend this to a supervised learning case where you get to see an x and then predict a y based on x, and c is some function from the class? I would say maybe. I don't know if you have any comments.
It seems like it would be a doable thing. I can't predict how the results would look, but yeah, we haven't really. But the notion of considering covariance would be good. I think it would require some modification of what we've done, but.
All right, so I'm sorry, we're out of time. I'm trying to keep on schedule. So let's thank the speaker again and take the questions offline.